Hello everyone, I am Akash. In today's video, we will solve an interesting MCQ question on abstract algebra from IIT JAM 2023 exam. Question is, consider the following statements. Statement 1 is, every infinite group has infinitely many subgroups. Statement 2 is, there are only finitely many non-isomorphic groups of given finite order. We need to examine whether these statements are true or false as given in options. Option A state that both 1 and 2 are true statement. Option B state that 1 is true and 2 is false statement. Option C state that second is true and 1 is false statement. Option D state that both 1 and 2 are false statements. So let's begin the solution. We will verify the second statement first. What is second statement? There are only finitely many non-isomorphic groups of given finite order. We know by definition of group that a group G is a non-empty set equipped with some binary operation, and that binary operation satisfies certain axioms like associativity, existence of identity, and existence of inverse. So by definition of group, we have a group G is some non-empty set equipped with some binary operation, say star. That is, star is a binary operation on G. This means that star is a function from G cross G to G. Okay. As star is a binary operation on G, this means that star is a function from G cross G to G. What is G cross G? G cross G is a Cartesian product of G with itself. If G has n elements, that is order of G is n, then G cross G has n square elements. Okay. If G has n elements, then G cross G has n square elements. And we know that the number of function from set A to set B is equals to the cardinality of B raised to power cardinality of A. So from here we have number of functions from G cross G to G is cardinality of B raised to power cardinality of A, that is n to the power n square. So there are n to the power n square functions from G cross G to G. But we know that every function from G cross G to G is a binary operation on G. Every function from G cross G to G is a binary operation on G. So from here we have, there are at most n to the power n square binary operations on a set G with n elements. Okay, since G has n elements. So from here we see that there are n to the power n square binary operation on a set G with n elements. So if the set G has n elements, then there are at most n to the power n square binary operations on G. And we know that for a G to be a group, there must be some binary operation associated with it. Okay, if for a G to be a group, there must be some binary operation on G. So from here we have, there are at most n to the power n square non-isomorphic groups of order n. Okay, non-isomorphic groups of order n means number of groups, non-isomorphic groups of order n means groups of order n up to isomorphism. Groups of order n up to isomorphism, that is, there are at most n to the power n square groups of order n up to isomorphism. So from here we have, there are finitely many, n to the power n square is finite number, so there are finitely many groups, finitely many non-isomorphic groups of order n. Okay, so but as n belongs to set of natural number is arbitrary, so from here we have there are only finitely many non-isomorphic groups of given finite order. Okay, so the statement 2 is true statement. Okay, so we see that the statement 2 is true statement. So option B is discarded because option B states that statement 2 is false, and option D is also discarded because option D states that statement 2 is false statements. So now we left with option A and C. For this we need to verify whether statement 1 is true or false. So let's verify it. Now we will prove that the statement in 1 is also a true statement. That is, every infinite group has infinitely many subgroups. So let's prove it. Proof of statement first. Okay. As we have to prove this statement for every infinite group, so let G be an infinite group. Okay, then each G belongs to G has at least one cyclic subgroup, namely subgroup generated by G. Then each element G belongs to G has at least one cyclic subgroup, namely subgroup generated by G itself, subgroup generated by that element itself. If G has infinitely many, distinct cyclic subgroups, then we are done. Okay, then we are done. Why? Because if G has infinitely many distinct cyclic subgroups, then G has infinitely many subgroups. So the statement 1 will be true. But what if G has only finitely many distinct cyclic subgroups? We have to consider that case too. Okay, so if G has only finitely many distinct cyclic subgroups, if G has only finitely many distinct cyclic subgroups, say H1, H2 and so on Hn, okay, then we must have at least one of these HIs, okay, at least one of these HIs must be infinite. Okay, why? If G has only finitely many distinct cyclic subgroups, say H1 up to so on Hn, then we must have at least one of these subgroups must be infinite, because otherwise if all of these HIs are finite, then we have G equals to union of HIs where I varying from 1 to n, because we know that every group can be written as union of all of its cyclic subgroups. As G has only these cyclic subgroups, so G can be written as union of H1 up to so on Hn, and as all of these HIs are finite, so this implies G is finite, and but we have G is infinite, so this implies G is finite and we get contradiction. So we must have at least one of these HIs must be infinite. Say H1 is infinite cyclic subgroup of G. Okay, we have considered at any one of these, say H1 is infinite cyclic subgroup of G, but this implies H1 isomorphic to Z with respect to addition, because we know that every infinite cyclic group is isomorphic to Z with respect to addition. And we know that Z with respect to addition has infinitely many subgroups, infinitely many cyclic subgroups. So H1 has infinitely many cyclic subgroups because H1 isomorphic to Z. So H1 has infinitely many cyclic subgroups. But H1 is a subgroup of G. So G has infinitely many cyclic subgroups. And as G has infinitely many cyclic subgroups, so G has infinitely many subgroups. So from here we have G has infinitely many subgroups, and this proves the statement 1. As G is arbitrary group, so we have every infinite group has infinitely many subgroups. So the statement 1 is also a true statement, and we have seen that statement 2 is true. So both the statements are true statement. So option A is correct. That is, both 1 and 2 are true statement. So if you found this video interesting and useful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.